All right, we're going to look at our double angle, half angle identities. There's a few other identities that we'll kind of touch on. We're not going to do a lot with, but the main ones that we're dealing with today are called the double angle and the half angle identities, and those are the ones that are listed, or the double angle identities are the ones that are listed up on top here. What I'd like you to notice right away is that there are actually three different things that we can replace cosine of 2u with. But sine and tangent both have only one thing that we can replace a double angle in those trig functions with. The first example that we're going to do here is to prove one of the double angle identities. We're going to prove the sine double angle identity, which I just wrote again right there, even though it's right there as well. We're going to start with the left-hand side, and we're going to work towards that right-hand side by using our sum formula for sine. So sine of 2u we can rewrite as the sine of u plus u, and then use our sum formula to expand that into the sine of u times the cosine of u plus the cosine of u times the sine of u. And really we have the same terms there that we're adding together. So what we have is two of them. We have two sine of u, cosine of u. The order of those factors doesn't matter, so I just put them both going the same way. And we have proven that sine double angle identity using the sine sum formula. The other, or some other identities that could become useful are the power reducing identities, which are listed right there. You are not going to have to know these offhand. We might prove them at some point in time during the homework or something. But it's a way to get rid of a quantity squared, a function being squared that does not involve the Pythagorean identities. So for example, if you have sine squared, you can rewrite it using this expression, and you don't have anything being squared anymore. But like I said, we're not going to use those a ton. All right, our next example here, we're going to prove that the cosine to the fourth minus sine to the fourth equals cosine of 2 theta. So what I'd like you to notice first is that we have a difference of perfect squares pattern because each of these are perfect squares. So I can factor that into cosine squared minus sine squared, or cosine, I'm going to go to the addition first, times cosine squared minus sine squared. So it's literally just like factoring something like a to the fourth minus b to the fourth. You're making that a squared plus b squared, a squared minus b squared. It's exactly what we've done. All right, now each of these has something that we can turn them into. Cosine squared plus sine squared, that should look pretty familiar. That's just equal to 1. And the cosine squared minus sine squared is one of our cosine double angle identities. So we can replace that with cosine of 2u, or 2 theta in this case. Now obviously this just equals cosine of 2 theta. So we've proven that identity. The third example here, we're not going to go through this one. This one's a little over the top. A lot of work with fractions and pulling fractional GCFs out. If you want to take a second to copy it down and kind of go through, the different pieces of it. I try to kind of color coordinate things that I was replacing with. But that's one that you can just look at on your own. I'd like to get to some of the other ones together here in the video. So now we're going to look at the half angle identity. So take a second to write these down if you don't have them down yet. Tangent in this case has 3 different half angle identities, and then clearly this is the one right here that we want to use most often when we are replacing this expression, because it's going to be the easiest one to simplify. Even though tangent of u over 2 equals any of those 3, the one in the middle there, that's the one that we're going to use if we have that choice. So one of the things that we're going to use the half-angle identities to do is to evaluate uh, angles that are half of an angle that we know the trig functions of. So for example, 3 pi over 8, I'm just going to move this down a little bit here so we can read this. 3 pi over 8 is not an angle that we know the trig functions of because we don't know its reference angle, pi over 8, we don't know its trig functions. However, we can rewrite 3 pi over 8 as 3 pi over 4 divided by 2. So this still says 3 pi over 8. It's the same thing. It's just that we are now putting a value in this spot right here that we do know all the trig values of. So because we're going to be dealing with 3 pi over 4, just somewhere maybe, how about right here? I'm just going to do a real quick sketch of where 3 pi over 4 is. 3 pi over 4 is in the second quadrant, has a reference angle of pi over 4. So I know that the cosine comma sine for 3 pi over 4, the cosine comma sine, well, they're both square root of 2 over 2, because the reference angle is pi over 4. Cosine in the second quadrant is negative, so we know that it's a negative cosine value. So that's going to come in handy as we're doing this here. So the first thing I'm going to do is use my half angle formula from up above, the cosine half angle formula right here. I just basically rewrote it without anything right here because I want to make sure that you put the right value right there. The value that you were dividing by 2 is the value that goes right here. So this is the point in this problem where you kind of need to stop and make sure that you know what this value is. If you don't, you pick the wrong angle to put right there. So make sure you know what the value of this trig function is right there. All right, let's talk about another piece in front of this here, this positive negative. That doesn't mean that our answer is going to be both positive and negative. It means you need to choose which one it should be. That is based off of the original function. 3 pi over 8 is in the first quadrant. That's less than pi over 2. 3 pi over 8 is like right there, okay? Because this would be 4 pi over 8. So we know the cosine in the first quadrant is positive, so I know that our sign that we want out in front there is positive. So I'm just going to circle it for right now, and then obviously since it's positive, I really don't need to write it anymore. I'm going to bring this thing down here now. Since it's positive, I'm not going to write that anymore. And then inside this radical, we want to now evaluate what the cosine of 3 pi over 4 is. Well, we just set up here that it's negative square root of 2 over 2. And this whole thing is being divided by 2. All right, so we know that plus the negative is going to be subtraction. So I'll take care of that in a second. What I'm also going to do, this is probably the biggest part of this whole step, is simplifying this. And this step that I'm going to use right now, we're going to use a lot. On the inside of the radical, we are going to multiply both the numerator and the denominator by 2. When we do that, we got to make sure we distribute that 2 to both terms in that numerator. Oops. So that it becomes, yeah, we'll take 2. I'm going to do this right here, actually. So that it becomes 2, and then I'll take care of that positive, negative, that plus minus becomes minus. When I distribute that 2 to the second term there, the 2 cancels out with the 2 in the denominator, and we're just left with the square root of 2 right there. And this is going to all be over 4. All right, so we did 2 really important things there. First of all, we got rid of this fraction. We no longer have that fraction, so that's nice. The other big thing is we made this a perfect square. The square root of 4 is 2, so we no longer need that radical in the denominator anymore. This is just going to become the square root of 2 minus the square root of 2 all over. Make sure you don't have that radical over the entire fraction. It's only over the numerator now, and the square root of 4 is 2. And this is a completely fine way to leave our final answer. It's okay that we have this here. This is okay. It's called a nested radical. We are not going to worry about simplifying that. But the other thing that I'd like you to see is how our textbook will often write our answer is instead of dividing by that 2, they'll put a 1/2 out in front. And so quite often you'll see this is the answer. Either one of these is okay. Either one of these 2 answers is a totally fine way to leave your answer. And this is the exact value of the cosine of 3 pi over 8. So without using a calculator, we are able to evaluate a function whose reference angle is not one of the big three. Okay, the next problem here, tangent of 67.5 degrees. We need to figure out what we can divide 67.5 degrees by in order to make it, or what we can divide by 2 to get 67.5. So to do that, you multiply 67.5 by 2 to figure out what goes up in the numerator. Well, that would be 135. So 135 degrees is the value that we're going to use as our u value or theta value, whatever we want to call it. It's this going to be this guy right here and right here. That's what we just decided. Or I should point out that one. We made that one 135, so these are both 135 then. Okay, so let's now use that middle tangent formula. This is going to be the easiest one to simplify. So we've got 1 minus the cosine of 135 all over the sine of 135. All right, so 135, actually here's the nice thing with these two examples. 135 degrees is the same thing as 3 pi over 4. So this little guy that we wrote right here works for both of these problems. We know the cosine is negative square root of 2 over 2. So we have negative square root of 2 over 2. And actually, let's be smart about this. Let's just call that plus square root of 2 over 2 right away, minus a negative. And that's going to be over the sine of 135, which is the square root of 2 over 2. Okay, so a couple ways you can handle this right now. If you want to get rid of the fractions all right away, do what we did in the last problem. Multiply everything by 2 first. Don't worry about the square roots yet. We'll take care of that in a second. And that'll give us 2 plus square root of 2 all over just the square root of 2. I have no idea why I'm making those blue, but there you go. Okay, put little equals there to show that's my next expression. By the way, that is something that a lot of us forget as we're doing these problems, and I'm looking at either your homework or even the quiz, that we just randomly have expressions all over the place. Trying to work in a manner that is easy for not only me to follow, but for you to follow so you don't get lost. And then using these equal signs to show your different steps. Okay, now we'll worry about that radical there. We're going to multiply both the numerator and denominator by the square root of 2. And we'll make sure we distribute that then in the numerator. So that's going to become 2 square roots of 2 plus 2 all over 2. And then we can simplify because there's a common factor of 2 in every one of those terms. Really what you're doing is you're pulling out a 2 in the numerator, leaving you with the square root of 2 plus 1. You have the 2 in the denominator, and those will cancel out. So we're just left with the square root of 2 plus 1, or 1 plus the square root of 2. There's our final answer there. All right, we're going to finish this up with some solving. I only have one example here, but try to leave some space over here to do another example that we're just going to add in here. Actually, it'll be a problem off your review. It's going to be number 45 off the, that's a number 45 off of the 5.34 review. And I think I left that problem on there this year. If I didn't, then we'll just use it as an example here. Okay, so now we're going to do some solving here. You want to get rid of any half-angle double angles with the identities that you learned today. So I want to point out this first thing here. Notice you have a half angle that's being squared. Remember, when you have something being squared, it means that the entire function is being squared. That's really what that thing means right there. It's the sine of x over 2 squared. So what I'm going to do is I'm going to rewrite that. Here's my left side. Now this is a solving problem. We're not working from the left to the right. We're writing both sides, and then going to work to get everything on one side, set equal to 0, factor if we can. All right, so sine of x over 2, I'm using this right here, so I could either put a little 2 right there, or I could write this thing twice, since that's what squared means, and that's actually what I'm going to do here. Um, Actually, I think you guys can handle this. You guys are mathletes, you can handle this. So I'm just going to leave that 2 there. Now we're going to replace that with the half angle formula. Okay, so it's the square root of 1. Since it's a half angle for sine, I know it's minus cosine of x, and that's all over 2. So I just replaced that with the half angle formula. Okay, now the nice thing is we're squaring it, so that big radical is going to go away. A positive negative squared, that's just positive. It doesn't matter which one it is. So we have 2 times, now that's still got to stay in parentheses here, 1 minus the cosine of x over 2. So that radical and that square just basically canceled out right there. And on the left side we have sine of x squared. And then these 2's, they cancel out. All right, notice what we have here now. We have sine squared, and then over here we have a cosine. Okay? We want to have the same trig function if possible. So let's get rid of that sine squared at this point in time. Let's call this thing 1 minus cosine squared so that we only have cosine functions here. I think that would be the thing that most students get locked up with here. You go through all this work with the half angle identity, and then you get here and you don't know what to do with these different functions. Don't forget your Pythagorean. Get one function if possible. That's what I have here. I'm going to get everything on the same side set equal to 0. So I'm going to add that cosine squared over so it stays positive. I'm going to subtract that 1. Actually, so the 1's are going to cancel out then. I have minus cosine of x. And then I'm just going to pull out a GCF there. And we have cosine of x minus 1 left in that parentheses. All right, so we're ready to use our zero product property. Set each of these guys equal to 0. Cosine of x equals 0. And we have cosine of x minus 1 equals 0. So cosine of x is going to equal 1. So we're talking about where cosine is 1 and where cosine is 0. Cosine is 1 right here at 1, 0. So we're at 0 radians because the point is 1 comma 0. And oops, I've got this mixed up, don't I? Got my colors mixed up. Let's fix that. Cosine equals 0 at pi over 2 and at 3 pi over 2 because we have 0 comma 1 and we have 0 comma negative 1. So at 0 and at put 0, darn it, pi over 2 and at 3 pi over 2, those are answers to this guy right here. I'm even going to write that over here. X equals pi over 2, 3 pi over 2. All right, cosine of x equals 1 only at 0 because of the point 1 comma 0. Okay, you don't want to include pi because cosine is actually a negative 1 there. So we have x equals 0 there. Now, probably a good idea to check up here. They don't tell us if they want the general to find all solutions or if they want to find it on the interval. Since they don't specify to find it on an interval, that means they want us to find all the solutions. So, is there any way I can include all these solutions in one statement? Can I get from here to here and then from here to here and then back to there using the same amount? No, I can't. So I think we're kind of on an island with this 0 here. We're going to cover all the angles that are coterminal to 0 simply by adding 2n pi to that guy. But we can find all the solutions to the y-axis solutions, pi over 2 and 3 pi over 2, by just starting with pi over 2 and then adding multiples of pi. That would cover both those. Okay, and then just to simplify this a little bit more, what we could do is get rid of that 0 plus and just say that our solutions are 2n pi and pi over 2 plus n pi. That'd be our solutions there. All right. Number 45 from your review packet. Actually, let me just make sure that we even have that one. If we do, made this new this year. Oh, that's nice. Maybe I should use a different version of this. Number 45. Hey, there it is. Ooh, I didn't leave you guys very much room here. I have to write small on this. Okay, here we go. If you want to do it on the notes, you can. If you want to do it here, you can. I'm just going to do this on our review since I've got it right here. So, first what we need to do is get rid of that. Cosine of 2x, I can use any of the three cosine double angle formulas. The one that makes the most sense is 1 minus 2 sine squared. That's what that becomes because, oops. Can I not move that thing? No. Because now I have all sines. So it's going to be some factoring again. Let's get, I'm going to get everything on this side, make that quadratic positive. So it's like I move both these over to there, but then I just flip my equation around so the equals 0 is on the right. So we've got 2 sine squared minus sine minus 1. Just making sure that that looks good. And now we're going to factor here. All right, so we have 2 sine of x, sine of x. And then I need factors of 1 here. One's got to be positive, one's got to be negative. Since I need it to add up to negative sine of x, I probably want this to be negative and this to be positive, because remember, these are the products that you're adding together. This would give me negative 2 sine of x here, this would give me positive sine of x, and those would add up to the negative sine of x that I have right there. So those are the products you want to check when you're factoring. So we're going to set each of these equal to 0. So I've got this guy right here is going to become sine of x equals negative 1/2. And then this guy is going to become sine of x equals 1 after I set them equal to 0 and solve for that trig function. All right, so I'm just going to do a little sketch right here. I'm going to put both of them on it. Sine of x equals negative 1/2 means our reference angle is going to be pi over 6, where sine is negative. Okay, sine is negative in the third and fourth quadrant. So we've got pi over 6 as a reference angle there, pi over 6 as a reference angle there. All right, so that would be 7 pi over 6, and that would be 11 pi over 6. Okay, sine of x equaling 1. Well, let's think about where sine equals 1. This is the point 0, 1 right here. So that means that sine of x equals 1. I'm going to get rid of that and just say this is where sine of x equals 1. So this is kind of a unique problem. That's at pi over 2. I got to zoom out here just to make sure. Okay, we're finding just the answers on the interval. Oh, that's boring. So we're just going to list these out then. Okay, and then we're going to talk about what if it was asking us to find. So these would be my solutions right now. Pi over 2, 7 pi over 6, and 11 pi over 6. Okay, so this is it. We're done. We don't have to do anything further with this problem. These would be our 3 solutions in one trip around the unit circle, one trip from 0 to 2 pi. Okay, if this were asking us to find all solutions, I just want you to notice that these can be, all 3 can be covered in one statement, because it would be the same amount to get from here to here as it would, it looks like it at least. I mean, the symmetry looks like it'd be the same amount. Let's just verify that it is. From pi over 2 to 7 pi over 6, I would need pi over 2 plus another pi over 6, which would be, let's get a common denominator here, 3 pi over 6 plus pi over 6. That would be 4 pi over 6, or 2 pi over 3. That's what this is from here to here, 2 pi over 3. Well, if I had 2 pi over 3, and obviously that's the same amount to get back there, so there's no question there that this is also 2 pi over 3 right here. Let's see if that's the same amount to get from 7 pi over 6 to 11 pi over 6. Well, if we think back to what it was as 4 pi, as being out of 6, 4 pi over 6, then we would get the 11 pi over 6. So we know that this is also 2 pi over 3 right here. So we are adding that same amount every time. We would just be able to start with, you always want to start with the smallest acute angle, so that would be pi over 2. And then we would add multiples of 2 pi over 3. So 2n pi over 3. This would be the solutions if we were asked to find all solutions, which they're not in this problem, but I just thought that that would be a good thing to talk about, simplifying those answers.